Right. Well, now we've seen actually quite a bit about how one does entropy extraction and then turns that extracted entropy into a key derivation function using a pipeline, something like this. So let's go ahead and formalize what a KDF actually is. So fix a set cal x, which is a subset of bit strings. This is going to be the sample space we've been talking about all along. A set calligraphic C, which is also a set of bit strings. This is the context space. This is the context info we were talking about. And some integer s, which is at least 0. Then a key derivation function is a mapping. So in particular, it's a deterministic mapping. It's a mapping from s, which is going to be the seed randomness. It takes in a seed. It takes in an element from the sample space. It takes in some context and a number. And it outputs either a string or an error symbol. And it has the property that if you call a KDF on a seed sigma, source sample x, some context c with a length l, you're guaranteed that the output of this will either be a string of length l or the error symbol. And this is for all possible inputs you give. All right, so let's talk about security for a KDF. We kind of already intuitively know what it is, but let's go ahead and formalize it. So let's let SAMP, this small caps SAMP, be a randomized process that outputs a pair, x and alpha, where x is what we've been talking about as the sample from the entropy source, which is non-uniform, but it gives us some kind of min entropy. And alpha is a string you can think of as being side information that's leaked about x. And this will be important in applications I'll explain in a minute. The security experiment that I'm going to define for KDFs then. So given a KDF and this SAMP. So SAMP is a randomized process that outputs a sample. So you can think about this as being the algorithm that samples from a distribution and provides the sample and some side information in the process. So given a KDF and sample, the randomness experiment for this pair for an adversary A is given as follows. We have a challenge bit B, which we flip. We run the sampling procedure to give us a source sample and the side information. And we pick a seed for the KDF from S-bit strings. And then we run the adversary A. And we give it the seed, as we've been talking about before. Even a good extractor, even if I show you the seed randomness and the output of extractor, you shouldn't be able to distinguish that from the seed and the truly random string. So we give it the seed. We also provide it the side information that we give it that came out as a result of us sampling this value. And then we give it two oracles. One of them is an oracle. Maybe zoom in a little bit here. So one of them is an oracle for this is the seed and the sample. And so the KDF is going to run with that seed and with that sample. And the adversary can call this oracle on two inputs. Well, those two inputs are going to be the context, the C, and the length of the output, L. So it gets one oracle that gives it true KDF outputs given that seed that it already knows and the actual secret sample that we're extracting keys from. That's one oracle. The other oracle is the challenge oracle. And the challenge oracle takes in a context and a length, and it picks string z of length L. This is what the KDF, you hope it returns, something that looks just like a uniform string. If the challenge bit B is equal to 0, well, we skip this step and we just return that random L-bit string. If the challenge bit is 1, then instead we actually run the KDF with the seed and the source sample, but with the context and the length that the adversary provides. So it's either getting the two of the same oracles, the KDF that lets it specify C and L, and the KDF specifying C and L, or it gets the KDF and an oracle that just returns a random bit string of an appropriate length. And, as you might expect, the adversary's job is to determine which of those two was the case. In other words, even given the ability to see outputs of the KDF, given a context and a length of its choosing, it shouldn't be able to distinguish between the actual KDF and a uniform random string. That's the experiment. We'll have to have a restriction here to prevent a trivial win, and that is that the adversary can't call this oracle and this oracle on the same context. It can call it on the same length if it wants to. We don't care about that. But if it called it on the same context, these two oracles, then we can't really expect that the KDF is going to behave differently. In particular, if it called it on the same CNL in both cases, then if the bit's 1, it's going to get the same result, because remember, the KDF is deterministic. So we forbid this kind of a trivial win, and we say that you're not allowed to call the true KDF oracle and the challenge oracle on the same context. And this makes sense because what we've been saying all along is you should be using different keys for different contexts. And so what this security notion is capturing is you can see KDF outputs on contexts of your choosing, but you shouldn't be able to look at those KDF outputs and then look at a key that's produced under a different context and distinguish that one from uniform. In other words, seeing lots of KDF outputs doesn't help you to distinguish some other KDF output with a different context from a uniform random string. There's our security notion. Let's talk about this side information. So what might this be? Well, it might be, for example, that the actual extraction process maybe leaks a little something about what those bits were that's sampled. But there are some cases where the side information may be a lot. So if we go all the way back to the beginning, where I was talking about processes where you might have to actually derive keys, a shared key between a client app and a remote server, from the transcript of messages that were passed. Well, this transcript of messages, of course, this isn't the real syntax, right? This was informal just to get us started. But the transcript of messages, it's got some client-side randomness in messages coming from the client. It's got some server-side randomness coming from the server. But this is all in public view. So you can think about this as side information related to the randomness that's contributed from these two servers. So that's what alpha is capturing, is whatever it is that the adversary learns about the actual entropy that's being used as a result of observing things, whether that be from observing a physical process or from observing some protocol that's been carried out. So that's the purpose of this alpha. And SAMP is basically saying there's some source sample and there's some side information about the source sample. And even given this side information, you shouldn't be able to distinguish keys under a context that you haven't yet seen from truly random bit strings. No efficient test should be able to do that. That's the KDF experiment. And if you think about it, it's not hard to see, at least intuitively, that the extract and expand KDF construction that we looked at up here, so I'll just pull it up, this thing, this is going to achieve this notion so long as your extractor is good, meaning that the master key is very close to uniform, because if the master key is very close to uniform, then our PRF is getting keyed by a uniform key effectively. And if the PRF is good, then everything that comes out of the PRF, particularly if you're calling it on distinct context information, this should be computationally indistinguishable from uniform. That's what a PRF does. So it's not hard to see that if you have a good extractor, if you have a good variable output length PRF, assuming that the side information doesn't leak completely what the source sample was, right? Because if alpha is X, for example, if it leaks the entire thing, then of course you're going to be able to distinguish these, because if that means you know all of the inputs now. You know the seed. If alpha tells you all of X, then you know precisely what this is going to compute for any CNL, because the KDF is deterministic. So as long as alpha is not leaking too much about what the source sample was, and you have a good extractor and a good variable output like PRF, it's not hard to see that this construction will achieve this notion. And you expect actually some kind of a bound like the PRF security of F for some adversary B that would just simulate the rest of the experiment. How good the PRF is plus how good the extractor is. You expect to bound something like this. All right, well, let me say a little bit more about this. This is the last part of this lecture. There is a construction which appears in TLS 1.3, which is the newest version of TLS 1.3. It's called HKDF. It appears in that paper I referenced earlier. HKDF stands for HMAC-based KDF, and we recently saw HMAC. HMAC gives us a variable input length PRF. But you'll recall the HMAC construction, there's this inner processing rail which processes most of the input. And that inner rail, you can in fact prove, is an epsilon almost universal hash. So HMAC in some ways is naturally a way to build under this extract and expand paradigm. This is the HKDF instruction. So HKDF as a primitive takes in, this is the seed, the extraction seed. This is the source sample, which they call the secret key material. So you've got the seed, the source sample, the context info, and the length of the output. And it returns this concatenated string of keys, where these keys are defined as follows. Well, the first thing you do is you use HMAC with the seed and the source. Well, this is exactly the extract part. And here we're using the fact that HMAC is a good epsilon almost universal hash, at least the inner part is, and then that's enveloped in a final compression function call that we modeled as being a PRF. So you remain a good epsilon almost universal hash. So this is the extract part. That produces this master key. The master key is then used in HMAC. So this thing should now be statistically close to uniform. So now we're keying HMAC with a uniform key, which is exactly what HMAC needs if you're going to use it as a PRF. With the context info, concat with 0 to get the first key. And then subsequently, you use that same master key, but the input is now the previous key, ki. So you start with k1, concat the context info, concat with the number, which is now 2. And that gives you key number 2. For key number 3, you use key number 2, the context info, and 3, right? So you're just getting domain separation out of this. And this is how you generate an arbitrary, this is a variable output length PRF that's being keyed by the output of the extractor. This is the HKDF construction. And if you go and look at that paper, there's a nice proof in there that this thing actually does achieve KDF security. I did want to make one final note, and that is all along we've been talking about entropy and min entropy and having the source that provides entropy of some kind. Well, entropy is an information theoretic measure, whether it's Shannon entropy or min entropy. These are information theoretic measures, and they say, because they're information theoretic, that, for example, in the case of min entropy, if you have min entropy M, that says no guessing algorithm, even a computationally unbounded one, can guess the outcome of a sample from this distribution with probability better than 2 to the minus m. Okay, but let's look at the very opening when I was talking about a client and a remote server having this exchange of messages. And at the end of it, you want to run your KDF on, well, in this case, you'd be running it. This source key material is actually just a function of those messages that were exchanged that contain entropy from the client side in some cases and entropy from the server side in other cases. But the catch is that if an adversary is allowed to see all the messages that go back and forth, and there can't be any additional randomness that goes into the KDF because both sides have to be able to create the same shared key. That means all of the randomness that's going into the KDF comes from the messages which the adversary saw. So if you allow the adversary to be computationally unbounded, there is no actual entropy that is left. There's no more randomness. The adversary has seen all of the random bits. And if it's computationally unbounded, there's nothing left. There is no true entropy that's left when you run the KDF. So it seems like this whole hour and a half long lecture is for naught if you want to apply in that application, because you had no entropy to start with, not even min entropy, truly, to start with. Turns out that's okay, because there are notions of what are called computational entropy, which is to say, yes, this string, which is the concatenation of all these protocol messages, doesn't have any entropy left in the true information theoretic sense. But if I restrict to a computational adversary, computationally bounded one, then I have effectively entropy. In other words, I have bits in that transcript that for a computationally bounded adversary are random. And these notions of computational entropy, in particular computational min entropy, are really interesting. If you want to know about those, I'm happy to share papers about that. But you can use computational min entropy in place of everywhere that we've said min entropy in this lecture, and all the same results work. So you're still able to extract a key which is computationally delta close to uniform, meaning no efficient test can distinguish the output of the KDF from a uniform random string. No computationally efficient test can. Everything else just goes through. So the whole extract then expand paradigm works, even in the case that all of the entropy is basically gone, as long as you restrict to computationally bounded adversaries, which is what we have in reality anyway. So I just wanted to kind of point that out in case anybody was listening was thinking, yeah, but if you see all the messages, there's no actual entropy, it's okay. That's a bit of an advanced topic. We're not going to get into computational entropy in the class, but I thought I would at least point it out if you're interested to read further.